Today we are going to discuss the topic whirling of shaft. So these are the table of contents: whirling of shaft, critical speed, problem and explanation. So first we are telling about whirling of shaft. This is also called critical or whirling speed of shaft. So simply defining the speed at which the shaft runs so that the additional deflection of the shaft from axis of rotation becomes infinite is known as critical or whirling speed. And here we are telling it occurs when the natural frequency of system coincides with the external forcing frequency. Means the critical speed occurs when the condition of resonance occurs. Means at a resonance condition, the speed corresponding is critical speed. So here at what we are explaining is here we are considering a shaft. Means two cases of shaft. Once the shaft, first case is shaft is stationary, second case is shaft is rotating. So here you can see two terms C and G. So C means center of rotor, the vertical member, and G means the center of the shaft. And you can see here the center of the shaft and the center of the rotor both are at a distance E. E is called the eccentricity. And when the shaft starts to rotate, the center of gravity or center of the rotor and shaft shift from the initial position to a new position. Means C and G shift from the initial axis to the new position, and the new position it is producing a deflection Y. Y means the extra deflection. Means here the Y means the deflection produced due to rotation of the shaft. So in the initial case, when the shaft is not rotating, when the shaft is stationary, there acts a centrifugal force, that is m omega square E. And when the shaft starts to rotate, in addition to eccentricity, there is an additional deflection produced, that is Y. So the total centrifugal force, that is m omega square into Y plus E. And here you can see when the shaft is deflected from the initial position to a new position, means C is changing position from initial dotted line to a new position. And in the second figure, the initial dotted line is shown by a symbol O. So OC is the extra deflection produced due to rotation of the shaft, and CG is the eccentricity. And we can say here the shaft here, what we are can say is this, we can compare this shaft, this rotating shaft or the deflected shaft with a spring. What is the nature of a spring? When we are applying a force, the spring will expand, and at the same time there will develop a restoring force which will try to bring this spring to this initial position. Similar case is established here. Means here some points are here mentioned: K stiffness of shaft, A eccentricity, then Y additional deflection, then omega angular velocity of shaft, and speed of shaft in rpm, omega critical speed of shaft in radian per second. So here centrifugal force, total centrifugal force after the additional deflection is m omega square into Y plus E. And I told you the shaft behaves like a spring. So the restoring force of this shaft is given by K into Y. So equating both, we are getting m omega square into Y plus E equal to K into Y, or Y equal to omega square E by K by M minus omega square, or plus or minus E by omega N by omega whole square minus 1. That is K by M means omega N square. And one more thing I am telling here, what is plus or minus sign means, here you can see the shaft moves upward direction and also downward direction. So the upward direction we are giving a positive sign, downward direction we are giving a negative sign. So the additional deflection produced here given by Y is equal to plus or minus E by omega N by omega whole square minus 1. And suppose when omega N equal to omega, what happen means the condition of resonance will occur, which means the denominator term will become 0. So the value of Y will becomes infinity. And we can say here at that value, means omega N equal to omega, that value, at what speed the shaft is rotating, that is called the critical speed. So here we can replace omega N by omega C. So So the final equation in terms of critical speed means E by omega c by omega whole square minus 1. So the same, the natural angular frequency and critical speed is almost same. So finally we are getting nc by n whole square equal to plus or minus E by y. And the final critical whirling speed is omega c equal to omega n equal to root of k by m, and root of k by m, or we can substitute, means we already know mg equal to k delta. So from mg equal to k delta you can find like this: mg equal to k delta means delta equal to mg by k. So you uh, you can substitute, instead of root of k by m you can substitute root of g by delta also from the equation mg equal to k delta. So here nc is the critical speed or whirling speed in rps. So 2 pi nc equal to root of g by delta, or nc equal to 1 by 2 pi into root of g by delta, and here 2 pi g all we know. So nc equal to 0.4985 by delta. This is rps. So here you can see both whirling speed and natural frequency are same, but the only difference is that both have different units. So once we go to unit, you can see nc is in rps and fn is in cycle per second. And this is one more equation: additional deflection y due to dynamic load y equal to w1 by w1 delta, where w1 dynamic load, w point load. This equation you don't need to remember, we can do this thing in problem. So these are the main important formula when coming to whirling speed. Moment of inertia of solid shaft, that is pi d raised to 4 by 64, hollow pi into d0 raised to 4 minus di raised to 4 by 64, do outer diameter, di inner diameter. Then mass equal to area into length into density. Area is pi by 4 d square for solid, pi by 4 into d0 square minus di square for hollow. And frequency of vibration 0.4985 by square root of delta 1 plus delta 2 plus or plus etc plus delta s by 1.27. This is called Dengerle's formula. This equation you have already used in system with several masses in module 5. So static deflection can be found based on load condition. So once you know Fn, if you are multiplying it by 60, you will get the whirling speed. So next we are going to one problem. This one problem: a shaft is simply supported at its ends and is of 40 mm in diameter and 2.5 meter length. The shaft carries 3 point loads of masses 30, 70, 45 at 0.5, 1, 1.7 from the left support. The weight of the shaft per meter length 73.57 Newton. The Young's modulus 200 giganewton per meter square. Find the critical speed of the shaft. This is the problem. So first what we are doing is we are finding the moment of inertia, that is pi d raised to 4 by 64. Then deflection due to point load. This equation also I have given you as a table in module 5 in system with several masses. So delta 1 equal to w1 a square b square by 3 ei. So from the delta 1 you are getting, then due to delta 2, that is delta w2, that's also same equation. Then w3, third point load. And suppose it is due to UDL, means you can see here here 3 point load and 1 UDL. So due to UDL, this is the equation. This all equation I have given you in the table. You can refer in module 5. So delta is equal to 5 WL raised to 4 by 384 EI. So once you know delta 1, delta 2, delta 3, delta s, then natural frequency of n equal to 0.4985 by square root of delta 1 plus delta 2 plus delta 3 plus delta s by 1.27. So Fn we are getting. Once you get Fn, then at critical speed nc equal to 60 into Fn. So you are getting 242.2 rpm. Okay. So next problem: a 2-meter long shaft supported in flexible bearing at its ends carries 2 wheels each 45 kg. One wheel is located at center, whereas the other at a distance of 350 mm from the center towards left. Shaft dimensions: inner diameter 40, outer diameter 80. The density of shaft material 7800 kg per meter cube and E equal to 200 giganewton per meter square. Find whirling speed of shaft. So the same like problem only. First you are calculating moment of inertia. This is a hollow, so you are finding the moment of inertia of hollow shaft. Then mass per length you are calculating. That's the density equal to mass by volume. From that concept, mass equal to density into volume. Volume means area into length. So we are finding weight. Then static deflection, that is due to different point loads we are getting. Here there are 2 points loads at C and D. So delta 1 and delta 2, and finally one UDL. So due to UDL also we are finding. So same problem, only difference here is 2-point load instead of 3-point load. Here only 2-point load. Once you get all the deflection, you are using the final equation for frequency, Dengerle's formula. And once you get Dengerle's formula and once you get natural frequency, then whirling speed of shaft is same. Whirling speed of shaft and natural frequency in whirling speed of shaft in RPS and natural frequency are same. And once you get natural whirling speed of shaft in RPS, just multiply by 60, you are getting whirling speed in RPM. So this much is the today's section. Thank you.